So, welcome everyone to Fundamentals of Food Process Engineering. So, every Saturday we'll take this kind of a doubt clearing session where we'll be discussing problems related to that week's syllabus. And these problems will help you in solving the assignments that are currently given to you right now. So, everybody can hear me?
Yes,
Okay, thank you. So, in case you guys have any doubts or if you want me to go slow or repeat something, you can let me know. You can just unmute yourself and let me know. Okay, so we'll move on to the first question. But before that, in case of any doubts, you can mail me through this mail or you can post it in the discussion forum where one of the TAs will answer your questions. So, moving on to the first question. In Herschel Berkeley's model, the intercept on shear stress axis at zero shear rate is called what? So, you have flow behavior index, consistency index, zero shear viscosity, and yield stress. So, what do you think is the answer? Any one of you? Does anyone know the answer for this question? Yeah, so the answer is yield stress. So for any fluid that require a certain amount of initial stress to start flowing, it will follow this Hershey-Berkeley's model. Berkeley's model. So here the shear stress is equal to tau naught plus k into shear rate raised to n. So when you look at the shear stress versus shear rate graph, you have a certain intercept, and then as the shear rate increases, the shear stress also increases. But this need not be a linear model. I'm just portraying you a linear model here. So in this formula, tau yz is shear stress, tau naught is the yield stress. That is the minimum stress that is required for the fluid to start flowing, which is also the intercept in this graph. K is the consistency index and N is the flow behavior index and gamma dot is the shear rate. So what kind of liquids do you think or fluids do you think require this yield stress? What is the name of those fluids called? What kind of liquids require an initial stress for it to start flowing? No, not Newtonian fluids. Think again. Newtonian fluids, all fluids start with uh, an intercept at origin. So there won't be any y-axis intercept. All Newtonian fluids will start from the origin. So the Bingham fluids, which are not Newtonian, they are in fact plastic fluids. All Bingham fluids have a profile exactly like this. So it will have an intercept here, and then as the shear rate increases, the shear stress increases, the shear rate will also increase. So an example of some of the fluids that follow a yield stress are Bingham fluids. So moving on to the next question. So the correct answer to this is option D. Moving on to the second question. In which fluid does the viscosity increase with increasing shear rate? So A dilatant, B pseudoplastic, C thixotropic and D rheopectic. Any other answer apart from pseudoplastic?
bureaucratic.
Any other answer? Why do you think it is rheopectic? So let us discuss each fluid one by one. So rheopectic, if you go, the viscosity does increase, but with time, not with shear rate. So at a constant shear rate, sorry, at a constant stress, I'm sorry, yeah, at a constant shear rate, the viscosity keeps on increasing and the shear rate also keeps on increasing. So this is a time dependent rheological behavior, and so is thixotropic. So both thixo and rheo are time dependent behaviors, whereas dilatant and pseudoplastic are time independent behavior. So rheopectic does have an increase in viscosity, but with time. Thixotropic has a viscosity decrease, but with time. And pseudoplastic, just a minute. So, and pseudoplastic also decreases viscosity, but with increasing shear rate. And dilatant is the one that undergoes an increase in viscosity with increasing shear rate. Or else, to summarize, dilatant are shear thickening fluids that experience an increased internal friction with increasing shear rate. So, as you give more shear rate, the internal friction between the molecules will also increase, and hence the apparent viscosity increases. So if you look at the shear stress and the shear rate graph here, so this is a shear thinning fluid which is a pseudoplastic. So as you can see, if you take the slope at each and every point, at some points you will see that the viscosity will slowly start decreasing. Whereas in case of a shear thickening fluid, if you take the slope at each point, you will see that the viscosity is slowly increasing with increase in shear rate. So these kinds of fluids where the viscosity increases with increasing shear rate are called dilatant fluid. And the reason why they are called dilatant fluid is because they, with increasing shear rate, they undergo an increase in volume. So if you take something like a fluid, a food fluid, where there are particles suspended in the liquid, when you give a certain shear stress, the liquid between those particles will squeeze and come out. So this kind of behavior results in increased friction. And since the squeezing results in liquid coming out, there is also a slight increase in volume. So this increase in volume is called dilatancy, and hence these fluids are called dilatant fluids. An example of this is cornstarch suspension. So if you initially cornstarch, if you keep on stirring it and give it an increasing shear rate, you will actually see that the fluid starts thickening. So viscosity increases in such dilatant fluids. So a correct answer to this question is option A. You guys have any doubts till now?
Oh, ma'am.
Okay. So if you want me to go a little bit slower, just let me know. So question 3. Which of the fluids have thixotropic behavior? A. Banana puree, concentrated fruit juice. B. Cornstarch, waxy starch. C. Toothpaste. D. Gelatin and egg white. So what do you guys think is the answer? Any other answers? You guys can either put it in the chat box or you can unmute yourself. Okay, can anybody tell me what is thixotropic here?
Excuse me.
Viscosity decreases, shear rate increases.
Okay, and is it a time dependent or a time independent process?
Time dependent.
Time dependent.
Okay, so why do you so the correct answer to this question is D, that is gelatin and egg white. So we'll go through each and every liquids here. So banana puree and concentrated fruit juice are actually shear thinning, that is pseudoplastic. They are time independent liquids and they undergo a viscosity decrease with increasing shear rate. In case of cornstarch and waxy starch, as we discussed in the previous slide, They belong to dilatant. They have an increasing viscosity with increasing shear rate. And toothpaste actually comes under Bingham fluids. So if you invert a toothpaste, a tube, it does not just start flowing. So you need to actually press it. You need to give an initial stress for it to start flowing. That is when a toothpaste starts flowing. So toothpaste comes under Bingham fluids. And gelatin and egg white are the ones that come under thixotropic behavior. That is, viscosity and shear stress decrease with time but at a constant shear strain. And this happens because over the time, the intermolecular interactions that are holding this egg white together kind of start breaking down. So with the breakdown of these intermolecular interactions, it is now easier for the fluid to move, and hence the viscosity decreases with time. Hence, gelatin and egg white are the correct answers to this question. Uh, Ajay, can you hear my voice? Is the mic yours not working or mine not working? Okay, so we'll proceed. In case you guys can't hear my voice, just let me know. Okay, moving on to the next question. So we'll look at two statements. You tell us whether if it is true or false. So statement 1, Young's modulus of elasticity is the ratio of longitudinal stress to the strain. So this is statement 1. And statement 2 is ratio of axial strain to transverse strain is Poisson's ratio. So which statement do you think is true? I mean, do you think these statements are true or false?
No, statement 2 is right. No.
Statement 2 is right. Okay, what about statement 1? So can anybody tell me what is Young's modulus of elasticity? You guys remember reading it in probably 11th or 12th or in the lecture videos as well. So ma'am would be explaining it again there.
Deformation of
Sorry, can you be a little louder?
forced deformation of biological material.
That is Young's modulus, is it?
Technical limit of elasticity that is used to specify the stress at which the permanent stress reaches a value of 0.2%.
We're not
But
looking at permanent any kind of stress here. So Young's modulus of elasticity is actually derived from Hooke's law. Do you guys remember Hooke's law? Okay. So Hooke's law states that there is a linear relation between stress and strain. So stress is directly proportional to strain. And when you remove this proportionality, there is an E value, that is the proportionality constant, which is known as modulus of elasticity or Young's modulus of elasticity. So in this case, it is generally considered that if you remove the stress, the material will come back to its original dimensions. So in Young's modulus of elasticity, you are generally giving either a tensile force, that is, you are pulling an object, or you are giving a compressive force, that is, pushing an object. So in either of these cases, you will see a difference in the length of the material. So in case you have something like a cylindrical object, if you pull the object, that is, if you give a tensile force, there will be an elongation of the object. So the length of the object will increase. Uh, on the contrary, if you give a compressive force, the length of the object will decrease. So this is where your modulus of elasticity comes in. So modulus of elasticity is stress by strain, that is longitudinal stress by strain. So this is applicable only when you are talking about tensile force or compressive force, not any kind of shear stress or so. So you will have actually a more detailed description of this in one of ma'am's classes, that is lecture 2. So there she'll be discussing about Young's modulus of elasticity. So in this case, since Young's modulus of elasticity is longitudinal stress by strain, statement 1 is correct. So moving on to statement 2, Poisson's ratio is actually the other way around. It is transverse strain divided by axial strain. So why there is a transverse strain is because this is also happening when you are having a tensile force or a compressive force. So when you're talking about longitudinal stress or strain, there is only a change in length. There is no change in volume. So if you're considering a block or a cylinder, let's say, and you're giving a tensile force, that is, you're trying to elongate the cylinder, but you're saying that the volume is not reducing. It means that the length is increasing, but somehow the diameter is decreasing. That is how it will compensate and make sure that the volume is same. Are you able to understand this? Yeah. So, are you able to understand? Sorry. Okay.
Yes, ma'am. It's clear.
Okay. So, since the volume remains to be constant, you will have something called an axial strain, that is an increase in length, and a transverse strain, that is decrease in diameter. So, Poisson's ratio is actually transverse strain divided by axial strain. So, statement 2 is false here. So, the correct answer to this question is option C. Moving on to the next question, it would be preferable if you guys have a calculator, because from now on we'll be dealing with numerical problems so that you will be able to answer the assignment questions that are given to you. Okay, we'll move on to the question 5. So, a cylindrical object of length 1.2 meter and diameter 5 millimeter is subject to a tensile force. That is, you're trying to elongate the cylindrical object. The length of the object is increased to 1.205 meter. Calculate the final diameter if the Poisson's ratio is 0.25. So you guys know, even if you don't have a calculator, can one of you tell me how to proceed with this kind of a problem?
No, we can use Poisson ratio. So Poisson ratio is nothing but transverse strain by axial strain.
Hmm.
Thereby length will be on the top and diametrical strain will be in the length diametrical will be on the top and the length will be on the bottom.
Correct.
So from
So
that ratio we can calculate.
do you know the formula for this? The exact formula?
No exact formula I don't know, but the strain will be like a. So what will be the length is already given 1.2 meter,
Hmm.
and the length of the object is increased to 1.205. From that we can calculate the transverse strain, sorry, axial strain. From that we can calculate as the axial strain.
Correct. So do you know the exact formula for how do you calculate strain? What is strain?
With delta L by L.
Correct. So axial strain is delta L by L and transverse strain is delta D by D, because there's a
Yes.
decrease in diameter. So you'll use the same equation that you explained right now. If anybody has a calculator, can you tell me the answer for this question? Is anybody calculating?
I am trying, madam.
Yeah. So the formula to this is Poisson's ratio is equal to delta D by D, the whole divided by delta L by L. So delta D by D is your transverse strain. Delta L by L is axial strain. So we'll move to the first step. That Poisson's ratio is transverse strain by axial strain. Mm, Can you please mute your microphone? You can tell me your answer when you are done. Okay. So Poisson's ratio is transverse strain by axial strain. So how do you calculate axial strain is actually delta L by L. So delta L you calculate by L final minus L initial. So delta L in this case will be 1.205 meter, that is your final, minus 1.2 meter. So your delta L, that is the amount it has elongated, is 0.005 meters. So axial strain you calculate by delta L divided by L initial. So you get 0.005 divided by 1.2 meters, which is 4.167 into 10 power minus 3 meters. Did you get this?
Yes, madam.
Is it clear to everybody else? Is this part? Okay. So moving on to the next step of this. So you are going to substitute this in Poisson's ratio formula, which is 0.25 equal to transverse strain divided by the axial strain that you just calculated. So if you do that, you will get a transverse strain of 1.042 into 10 power minus 3. And after this, transverse strain is delta D by D. So if you already know the diameter that is given as 5 millimeters. So you need to convert that into meters and calculate delta D. So delta D comes out to be 5.21 into 10 power minus 3 meters. So in this case, does the diameter decrease or increase?
Decrease, madam.
Okay, yeah. So in this case, instead of final minus initial, delta D will be D initial minus D final. So if you calculate 0.005 will be your delta D, will be your D initial minus 5.21 into 10 power minus 3 will be your delta D. So total delta D final is 0.4995 millimeters. So the answer to this question is option B. Did you guys understand this? Can I proceed with this? Is the answer clear? Okay, we'll proceed with the next question. So question 6. A liquid of viscosity 20 pascal second is filled between two plates of a surface area of 0.01 meter square separated by a distance of 1 centimeter and moving with a relative velocity of 1.5 meter per second. Here the sheet is moving, that is the plate is moving at a relative velocity of 1.5 meter per second. So what is the force required here? Any idea how to calculate this? So you actually have two plates here separated by a height of 0.01 meter, and it is moving at 1.5 meter per second. So how do you calculate the force that is required to move the plate? Any clue? I don't want to answer. If anybody knows how to calculate. Okay, we'll move to the solution part of this. I'll stop in between so that you can ask any doubts if you have. So here, when you give a shear stress to some object, it will generally move a distance. So here, the distance it has moved is dl, and the height between these two plates is 0.01. So when you apply a shear stress, the shear strain can be given by gamma. So that gamma is actually dl divided by this height, which is the tan gamma is your shear strain. Okay, so tan gamma is dl tan gamma, which is equal to the shear strain, is dl divided by 0.01 meters, which is your height between the plates. So if you want to require the shear rate, that is gamma dot, that is equal to d gamma by dt. So as you know, I have said here gamma is equal to dl divided by h. So if you substitute gamma here, you will have d by dt of dl by h. So h you can take out of the derivative. So dl by dt will be equal to velocity. So here the shear strain is equal to velocity, shear strain rate is equal to velocity by height. Are you guys able to understand this? This is actually a part of lecture 3 in the week. Are you guys clear with this? So given this equation, can you now calculate what is the force required? Do you know how to proceed with it? So you'll be applying Newton's law of viscosity here. So first we'll calculate shear strain rate here, which is equal to V by H. So you know that the plate is moving at a velocity of 1.5 meter per second, and the height between the two plates, or the distance between the two plates, is 0.01. So the total shear strain rate is equal to 150 second inverse. So using Newton's law, which is equal to shear stress is directly proportional to shear strain, we have F by A is equal to mu into gamma dot. F by A here is the shear stress, gamma dot is the shear strain rate. So now can you guys calculate and tell me what the force is? Yeah, so the answer to this question is 30 newtons. So if you substitute the area 0.01 meter square is equal to viscosity into the shear strain rate. So that is equal to 30 newtons. So the correct answer to this question is option A. So all this is a part of lecture 3. In case you guys want a more elaborate explanation, ma'am would be giving you all these information in lecture 3. So moving on to the next question. Density and the kinematic viscosity of a fluid is 1000 kg per meter cube and 10 power minus 5 meter square per second. Calculate the dynamic viscosity. This would actually be in your assignment 0 as well. So if you guys have solved assignment 0, this would be easy. So what is the relationship between kinematic viscosity, density and dynamic viscosity? Anybody knows the relationship between all these three parameters?
The kinematic viscosity is equal to dynamic viscosity by density of fluid.
Yeah, correct. So what is the dynamic viscosity according to the calculation here? If not in centipoise, can you tell me in Pascal second?
0.01 kilogram per meter second.
Okay, so that is in Pascal second. So what is the conversion between a Pascal second and centipoise? Anybody knows that? So 1 Pascal second is equal to 1000 centipoise. So what is the answer to this now?
10 centipoise.
Yeah. So kinematic viscosity is equal to dynamic viscosity by density. And if you substitute the values, you get 0.01 pascals. In other words, it is into 10 power 3 centipoise. That is 10 centipoise. So the correct answer to this question is option B. Moving on to question 8. So what is the relationship between Young's modulus and shear modulus if Poisson's ratio is 0? So this will also be a part of your lecture 3. Majority of these questions are from the lecture 3 only. 3 and 4. Anybody knows the general formula between Young's modulus and shear modulus? So you guys learned what is Young's modulus. Young's modulus comes into picture when you're talking about longitudinal strain. That is, you're giving a tensile force or a compressive force. So where does shear modulus come into picture? So I've got one answer. Anybody else? If you guys don't know what is shear modulus, you can ask me. So where do you think shear modulus comes into picture? So shear modulus comes into picture when you're applying a force tangential to the surface. I mean, you're applying along the surface rather than uh, what do you say? You're not compressing or you're not pulling the material. You're just giving it tangential to the surface. That is called a shear stress. And that shear stress is directly proportional to the strain that is causing in the material. So when you remove that proportionality, you get a proportionality constant that is known as shear modulus. So the relationship between Young's modulus and shear modulus is G equals to E by 2 into 1 plus mu, where G is the shear modulus, E is the Young's modulus, and mu is the Poisson's ratio. So when you apply mu equal to 0 here, you will be getting G equal to E by 2 as per all of you have answered. So the correct answer to this question is option A, which is G equal to E by 2. Moving on to the next question. The unit of bulk modulus is what? Yeah. So bulk modulus comes into picture when you're talking about compressive force. So your dV by V is equal to K into dP. Here K is just a proportionality constant. It is not the bulk modulus here. So K here is minus 1 by V dV by dP. And your bulk modulus is actually the reciprocal of this proportionality constant, which is minus V dP by dV. So the units of V and V cancel, and you have the units of pressure only, which is Newton per meter square. So as you guys told me, so a correct answer is option C. Moving on to the next question. A cylindrical object of length 1.2 meters and diameter 50 millimeter is subjected to a tensile force of 10 newtons. The length of the object is increased to 1.205 meter. So calculate the Young's modulus of elasticity. So can anybody tell me how to go about it?
So Young's modulus is equal to stress by strain.
Hmm. So here you do not
Stress
have the
equal to
stress.
force.
Yeah. So stress is equal to force divided by area.
Force by area. So we have diameter. From that we can calculate area. So 10 divided by area. Strain will be like a delta L divided by L.
Hmm.
From that we can calculate it.
So area is what? Cross-sectional area or your surface area, the curved surface area?
A cross-sectional area where that force perpendicular to.
Hmm. So when you calculate here, this is what is happening to the cylinder. Once which was 1.2 meter is taken is given a tensile force of 10 newtons, and the length is actually elongated to 1.205 meters. So as per you said, force by area is equal to Young's modulus into delta L by L. Well, force per area is the stress, delta L by L is strain. So delta L is L final minus L initial. So again you get delta L as 1.205 meter minus 1.2 meter, which is 5 millimeter in this case. So area is cross sectional area because you're giving a tensile force in that particular face of the object. So area is cross sectional area given by pi d square by 4. So your area should come out to be 1.96 into 10 power minus 3 meter square. Is anybody calculating? Shall we move on to the next step?
Yes, ma'am.
Okay. So you calculate Young's modulus by separately calculating the stress, which comes out to be force by area, that is 5092.96, and your strain comes out to be delta L by L, which is 4.167 into 10 power minus 3. So if you divide these two values, you get an Young's modulus of 1222 into 10 power 3 Newton per meter square. So your correct answer is option A, not option C here. So if anybody is calculating, did you get this answer or should I move on? You guys have any doubts till now? Okay, yeah, sorry. I understood it wrong. It's cross-section, right? This PPT will actually be sent to you. Hopefully, we'll be putting it in a Google Drive, and this entire lecture will also be available in YouTube pretty soon, but not immediately though. The YouTube will be video will be available probably today or tomorrow itself. I'm not sure about the Google Drive. Sorry, the slide PPT as such. That would be circulated by the NPTEL themselves. So moving on to question 11. So this is a bit more higher difficulty level. But this is kind of very close to your assignment question here. So the shear stress of 3 kilopascals is applied to a non-Newtonian fluid that results in a shear rate of 45-second inverse. The fluid has a consistency index of 1.5 kg per meter. So what is the apparent viscosity of the fluid assuming that the yield stress is 0 and the fluid follows power law? So anybody knows what the power law is? It's a more generalized version of the Newton's law of viscosity. Do you guys know what a power law is? All the assignment questions are, as of now, I saw only option based. I didn't see like typing the answer as such or showing your work. I'm not sure if it will come in the later assignments, but the two assignments that are uploaded right now are all MCQs. But it will involve calculation from your sides. There are numericals in the assignments. So the power law is basically stress equals to K into strain raised to N. So in case of Newtonian fluid, N is equal to 1. So you will have a stress directly proportional to the strain alone. But in case of non-Newtonian fluids, this N will actually have a value. So do you know what value does generally a shear thinning fluid has?
Less than 1.
Yeah. And a shear thickening fluid will have an N greater than 1. And to answer Ulanganathan's question, there is a time limit to send the assignments. It will be given on top of your assignment. The very first line in your web page itself will give you the deadline to finish. I think the first assignment has to be finished before 10th, if I'm right. You can attempt it multiple times, but your final attempt will be taken into consideration for grading. So yeah, so this is the power law. That is, shear stress is equal to K into dVx by dy raised to n, where K is the consistency index and n is the flow behavior index. So how do you go about calculating the apparent viscosity? Anybody has any answer? The answer is not 1. I mean, it's not the first option. Assignment 0, I don't think there is a deadline though. It's like a prerequisite that you need to know to understand the course better. So the assignment 0 solutions are both given in PDF format and it is also available in YouTube. So you can go and follow those any both of those. But it is better to submit your assignment 0 whether or not it is graded. I'm not sure if it is graded or not. But it's like a prerequisite and it is better to solve that before you go into solving assignment 1. So in order to calculate the viscosity, first you need to calculate what the n value is. Without that, calculation of viscosity is not possible. So you take a log on both sides. So you will have log tau yx equal to log k plus n log gamma dot. So if you plug in the values, you will get log 3 kilopascals is 3000 pascals equals to log 1.5 plus n log 45. So if you calculate this, your n should come close to 2. Is anybody calculating, or you guys understand what is going on? Is this part of the solution clear? The YouTube video you can just Google as fundamentals of food process engineering assignment 0. So I would have uploaded it would be in my channel. I would have uploaded the YouTube. If you want, I can send you the link later. I can post it in the discussion forum as well. You can take the link from there. I would generally be explaining all the step by step process, and the step by step process is also available in the form of a PDF format in the announcement sections in your course. So okay, so apparent viscosity, since it's a non-Newtonian fluid, this K is not actually equal to viscosity. If it was a Newtonian fluid, this K is actually equal to viscosity and N is equal to 1. Since it's a non-Newtonian fluid, the apparent viscosity is calculated by K into gamma raised to N minus 1. So if you plug in the values, you know what is the value of K, you know what is the value of gamma, given as 45 second inverse. So 1.5 into 45 raised to 2 minus 1 is 67.5 Pascal second. So actually power law will be useful in your assignment 1 right now. You need to know what each and every term here stands for. So the correct answer to this question is option D. So this is also available in your assignment 0, not the exact same question, but you will be using a similar method. A fluid of density 980 kg per meter cube is flowing through a pipe of 0.5 meter inner diameter. The length of the tube is 10 meter and the viscosity is 20 Pascal second. What should be the volumetric flow rate in the pipe to maintain a pressure drop of 7000 pascals, assuming that the flow is laminar? So what formula will you use? We will talk about the solution later. So anybody, did you solve assignment 0 till now? You will have the same kind of question there as well. So have you heard of Hagen-Poiseuille's equation? It is for fluid flow in a pipe for laminar flow behavior. So in Hagen-Poiseuille's equation, delta P, which is the pressure drop across the tube, is equal to 32 mu L V by d square, where mu is the viscosity, L is the length of the tube, V is the velocity in which the fluid is flowing, and d square is the diameter of the pipe. So if you plug in the values, we will have 7000 pascals equal to 32 into 20 into 10, substituting all the values, by d square. So once you get velocity, how do you calculate the volumetric flow rate?
Velocity into flow area.
Yeah, so velocity into flow area will give you the volumetric flow rate. So in this case, the flow area is actually the cross-sectional area. So velocity into cross-sectional area will give you the flow rate, which comes out to be 0.05 meter cube per second. So the correct answer to this question is option C. Do you guys want me to go a bit more slow, or are you guys understanding? Or is this very new to you? I would actually prefer answer here. Is this new to you? Is this like too much, or can we go a bit more slow? What is your opinion? Okay, so in case you guys find it difficult, you can always mail me back. I can send you some kind of more questions if you guys want, or we can take up all these doubts, any kind of doubts that you have in the next session as well. We'll have one every week, so you can either we can discuss it in the discussion forum, or we can take it up in the next class as well, where I can explain you step by step. Okay, so you guys have any other doubt, any feedback, anything? So my mail is bt18d700@smail.iitm.ac.in. Would you like to be a bit more slow, or are you saying that I have to pick up speed?